Question: how do we assess categorical arguments for validity? Well, now that we're getting ready to start this little quest, I figured it'd be a good idea for me to jump on the microphone here so you can hear my very soothing voice. This is sometimes a challenging task at first, so I want to make sure I ease you into this with plenty of examples, guided examples. Okay, so let's go ahead and get started. For any of this to make sense though, it really would be helpful for you to review the definitions that were found in the last homework assignment. So if you have not done that yet, please go check those out at least. Okay. As previously mentioned, we will be crawling before we are running. We will begin with immediate inferences, and we will use the square of opposition for this. There are other methods of doing this. We will use a square, so we'll talk more about that in a second. The main reason why I like to use the square of opposition, it relates the most to some of the ideas that we'll be covering later on. This is in a way a paper computer. We'll talk about that later. Stay tuned for that. But it is maybe the most relevant to the modern notion of computation, the square of opposition. So I like to do that one to kind of get you going. Okay, we won't be using that nice little diagram though. We'll be using a typical square of oppositions. Here it is, well, maybe I think it's more intimidating at first than it really should be. It's actually very simple. So let's start kind of teasing out some of these concepts. Let's begin with contradictories. And remember that the types of sentences are in the corners. So we have top left is an A-type sentence, bottom left is an I-type sentence, top right is an E-type sentence, and there at the bottom right is an O-type sentence. Okay, so the way contradictories work is they basically flip the truth value. If you know that you have a true A-type sentence, then you know that the diagonal, some S or not P, the O-type sentence, you know that it's false. So basically just if one is true, the other one's false. That goes for both contradictories. Let's just say we begin with a false I-type sentence. That means that the E-type sentence, that diagonal, is true. It just flips, right? One is false, the other one's true. Okay, contraries. Contraries can both be false, but they can't both be true. Subcontraries can both be true, but they can't both be false. If you need to, go ahead and maybe run through an example. Remember, S stands for subject, P stands for predicate. So you can give yourself any subject and predicate, maybe dogs and mammals. All dogs are mammals, right? And kind of use those same categories across these sentences, and you can see how this works. We'll go over an example in a second anyways, but just so you know, while you're on this screen, you can pause and think about it. Okay, let's do subalternation and superalternation. So the way that subalternation works is you begin up and you move downwards. That's why the arrow is pointing downwards. And the way it works is you have to start with a true A statement or a true E statement. Okay, so if you know that all S or P is true, that actually makes some S or P true as well. That's why the arrow is pointing downwards. But it only works with truth. It doesn't work with falsity. Okay, the one that does use falsity is superalternation. If you know, let's do for example the type O sentence there at the bottom right. If you know that some S or not P is false, you also know that no S or P is false. That's just the way it goes. It doesn't work for truth though. So that's how the table works in the abstract. Let's go through an actual example so we can get a better sense of how this works. I might add here this quick little note that there are various ways to assess immediate inferences for validity, such as the laws of conversion, aversion, and contraposition, or the use of Venn diagrams. We will cover only the square of opposition here. We will use Venn diagrams for categorical syllogisms later. Now, I might tell you why real quick. The laws of conversion, aversion, and contraposition are cumbersome, and it's very complicated, and it's really not that fun. So I don't like to teach that one. Again, the square opposition relates the most to some ideas that I want to cover later on in this class. We won't be using Venn diagrams though, and that is why you will dream of circles pretty soon. But let's wait on that until we have to do it. Okay, here are the steps for assessing immediate inferences. First of all, write out the argument. I have here a very simple immediate inference. Here we have a premise, that's a categorical proposition. The conclusion is also a categorical proposition. It looks good to go. By the way, technically I didn't do this in this case, but you can put these sentences into standard form before you engage in this activity. I'll go ahead and let you do that. I'm going to work with this sentence as it is for now. Okay. Step 2. Assess which type of sentence of categorical logic the statement is, and write the letter beside the premise and conclusion. We go back here to our argument, and we see that the premise, all reptiles are cold-blooded, that's just an A-type sentence. So, just so you can confirm, all F or G, that's what it says. It's an A-type sentence. Very good. And as for the conclusion, the categorical part of it, some reptiles are not cold-blooded, you can tell that that's an O-type sentence. And we label them and leave it at that. Okay, let's move on. Step 3. Write the truth value, either T or F, next to the sentence letter of both the premise and the conclusion. Note, if the sentence is just asserted, that means it's true. Okay, premise 1. All reptiles are cold-blooded. That is just asserted. It's stated as a fact. So we are going to assume it's true. The conclusion, it says right there that we're saying it's false. So we'll label it false. Lastly, step 4. Discover what the truth value of the premise implies. Okay, for this we have to use our dandy square of opposition finally, but I want to make sure it's clear what's going on here. Use the square of opposition to figure out the truth value of the rest of the sentences given the premise. But remember, use only the premise. The whole point of validity, the study of validity, is to answer the question, if I know this, do I also know this? So what we're really doing here is, if I know this premise, do I also know the conclusion? That's the whole point of this task. So we come to our square of opposition. Let me shrink this down real quick. Very good. Okay, and now we grab our premise and literally forget about the conclusion for a second. We don't need it, all right? It's just the premise. And we bring it over to our square and we put it in its rightful place. A-type sentence, top left, true. Okay, what else do we know now given that we have a true A-type sentence? Well, we do know the diagonal. If A is true, O is false. Very simple. We also know that we can use superalternation here. Superalternation is if the O-type sentence is false, the E is also false. Simple as that. And we can get that value of the I-type sentence through a variety of means. We could use subalternation. If A is true, I is true. Or we can use the contradictory again. If E is false, that means I is true. Either way, I is true. Okay, there is our square of opposition. That's what we know given the premise. Okay. Here it's time to check. Do the inferences that you made on your square of opposition match the conclusion of the argument? Well, here's the rule. check that the truth value of the conclusion matches the truth value for the relevant sentence type on your square of opposition. If they do match, the argument is valid. If not, it is invalid. Here I reproduced our square of opposition as well as our argument and the etchings on its side. We see here that our conclusion in the argument is a false O sentence. And in our square of opposition, we also have a false O sentence. That is a match, my friends, which means that this argument is valid. Very good, very fun, excellent times ahead. Okay, let's do one more example to make sure that you have this down. Now, some people are confused by these imaginary categories, kleps and foo. It doesn't really matter what it is. If you want to replace it with K and F, that's fine too. What matters is the steps. Remember, just like computers don't really know what you're typing, they just know what to do with the information. That's what you sort of want to turn yourself into here, a human computer. All you really want to do is follow the steps. I almost called it an algorithm. Follow the steps and you'll get the right answer. And that's how logic is. Okay, all kleps are foo. That's definitely an A-type sentence, and it's false. Good. As for the conclusion, it's a true I-type sentence. Some kleps are foo, and this is true right there. Excellent. So we take the premise information, a false A, and see what we know from there. This is an interesting case. Let's start with the contradictories. I always love to start in that way. It's just easy. You just flip the truth value. If you got a false, now it's true. Excellent. Okay, can we do anything else here? Well, superalternation would be useful here on the right-hand side if that O sentence is false. Superalternation works this way. If the O is false, the E is false. But we got a true down there. That means you don't know what that is. Contraries won't help either because they can both be false. So you don't know if it's true or false. You don't know what to label that E, hence it is undetermined. By the way, it's always the case that if you have one undetermined, you'll find another one diagonally across from it. It just turns out to be the case that in this particular argument, beginning with a false A sentence, this is all we can find out. All we really know is that we have a true O sentence. The rest are undetermined. So before long, you'll realize there's really a finite set of possible squares you can have. You actually memorize them if you do enough of these. In any case, what we need to do here is look at the conclusion. That's a true I. If I go back here, our square says we have an undetermined I. So given the premise information, we don't know what the truth value of I is. As such, this conclusion, my friends, does not match. It's invalid. That's how that works. You have some fun times ahead of you. Do many of these problems, and I think you'll get the hang of it. Email me if you have any questions, and read on. There's more to this lesson.